Hello, this is an actual Brayton cycle problem which builds upon the ideal cycle by adding a turbine efficiency and a compressor efficiency. We will leverage what we have done before in the previous video where we solved an ideal Brayton cycle problem and use that solution because every number here is the same except we have added compressor and turbine efficiencies. The compressor efficiency is given by the power produced by the ideal compressor, which is lower, which is proportional to H2 minus H1 divided by H3 minus H1 will be the actual compressor. So that helps us get an equation for H3 in terms of the corresponding isentropic problem. We are going to use this equation to find enthalpy at 3. Also for the turbine, we can write eta turbine, the turbine efficiency. In this case, the actual turbine produces less power, so it will be H6 minus H4, 6 being the actual exit state, and H5 minus H4 for the ideal turbine, giving us an equation for the actual turbine exit enthalpy, H4 plus H5 minus H4 times eta turbine. So these are the new states we introduced compared to the at state 3 and 6. These are the actual exit states of the compressor and turbine respectively. So first thing we'll do, we'll launch the test step, go to the test steps page and launch the vapor power and gas power cycle test steps using the PG model, and it comes to the hands-on examples page, and you can see the ideal solution is right there. The ideal turbine solution is right here. So you go copy the test code to jumpstart our solution, and why repeat everything we have done previously. Now we come to the test step page, paste the code here, click the load button, and do a super calculate just for the sake of it. You notice that we have reproduced our efficiency of 48%, net power, etc. of the ideal solution. So now, first thing first, let's go to the user codes and define what's our turbine efficiency and compressor efficiency are. The compressor efficiency is 90%, we'll call it 0.9 as a fraction, and turbine efficiency similarly is 0.8. We'll click the calculate button to register the change, and now let's go to the state panel. So state 2 is our isentropic state. So we want to introduce a new state here, state 3, and pressure is the same. It's not isentropic, but we know enthalpy, so we got to write an equation for enthalpy, which we already wrote down. H3 equals H1 plus H2 minus H1 divided by efficiency of the compressor. Hit enter. The solution is found here in the graphics panel. State 3 should be to the right of state 2 as we expect. Similarly, so let's go take a look at state 4. State 4 is P4 is the turbine inlet pressure, which is same as P2, that's correct. And maximum temperature is correct, so everything about state 4 looks nice. So state 5 is the isentropic state. To introduce state 6, the actual exit state, we click the plus button, which copies state 5, but state 6 is not isentropic. Instead, we know H6, the expression for H6, and let's type it in. H4 plus equals H4 plus H5 minus H4 times efficiency of the turbine. We click the enter button, the state is found. Let's go and check one more time in the graphics panel. So we should see the state should be 1, 2, 3, 4, 5, and 6 should be to the right of 5 as entropy has increased because of generation of entropy. Go to the device panel. Device 1 is our compressor, but it's not state 1 to 2. It should be state 1 to 3 because 3 is the actual compressor. And the combustion chamber or the heat exchanger should operate between 3 to 4. 3 is the actual compressor exit. Calculate. And the turbine should be from 3 to wait a minute. So the device 3, the turbine, it should go from 4 to 6. And finally, device 4 should be from 6. Now that all the devices have been analyzed, in the cycle panel, we can see that the cycle is complete and the thermal efficiency has been found, the net power has been calculated, and it must be equals, the net work must be equals net heat transfer. If we go to the I/O panel, the first sanity check will be what? That what if the efficiencies were 100%? Both of the efficiencies are 1 and 1. In that case, it should revert back to the ideal cycle. So we calculate this and super calculate, go back to the cycle panel, and 48.23. Recall that was our ideal cycle efficiency. So now it's so easy to do a parametric study. You go to the I/O panel and you can change your efficiencies. For instance, suppose we say the compressor efficiency is now 80% and the turbine efficiency is 90%, 0.8, I'm sorry. Change these values. We do a calculate in the I/O panel to register the changes. As you can see in the bottom panel, the registered value shows up. And then we go back to the, we just click super calculate and everything is ready for us. The efficiency is 33%.